Now the next would be, then we sum this all up for net irrigation requirement. The net irrigation requirement is going to be a summation of all of these things. Net irrigation requirement will equal the ET for the season plus leaching minus effective precipitation minus water stored. So we have two pluses, the ET and the leaching, that are going to have to be irrigated in. We subtract how much precipitation we get from that value, and we subtract the water stored that we've put in the previous crop year, or residual carryover water that was left in the soil from the previous crop year. So that will tell us how much irrigation we need to apply in a given year. And so we can plan our water. Not only can we plan our water, we can also plan our energy costs, because we'll know what it costs us to pump that amount of water, or if we're having to buy water, like if we're in the city and we're doing turf and we know we have to buy the water, we will have a real good idea of the total dollars in water use that we're going to have for this coming year by knowing how many acres of turf we have and how much net irrigation we're going to have. We know the price of water. We can calculate our water costs for the year. So it's a great management tool. Now, estimated evaporation or estimated evapotranspiration. We talked about the fact that there are mathematical models to do this with. And we talked a little bit about the Blaney-Criddle method, the Penman method, the Thornthwaite method, depending on the kind of climatic conditions you have. You know, is it arid, is it humid, amount of daylight hours, amount of temperature, amount of heat units are the things, these climatic, and wind are the climatic conditions that are going to affect this. I think we beat this up in the previous little discussion there. And then we've talked about also we have the pan evaporation, and we showed an example of pan evaporation. And so as we estimate, and again we can get very, very good estimations if an area has had pan measurements come out of it. So maybe we want to go to an area that has been typically dry land irrigated, and we want to look at doing some irrigated farming. Well, if there's a weather station in the neighborhood, we will have excellent pan evaporation data because somebody's been monitoring that for us. From those values, then we could determine what our water needs would be for a given crop, knowing what the multipliers are for the different crops that we might grow. I had a guy call me from an area, it's up around, or south in Oregon around Wasco, and he was looking at putting in a cherry orchard. All dryland wheat country up there, no irrigation within 20 or 30 miles of where he was looking at, but he wanted to know, well, how much water is it going to take? There's no irrigated crop data in the area. Well, there happened to be a weather station in the neighborhood, so I look at the pan information you get from that weather station, and you'll have a real good idea of what amounts of water you're going to need to irrigate cherries, because water is a very precious commodity apparently in that area. They drill wells and they don't get there's no surface water, so they're drilling wells and they're pretty limited on the amounts of water in that particular area, and he was wondering just how many acres could I water if I had 500 gallons a minute. Well, what do? We go to the worst year or the worst month and look at what the peak demand is. Oop, that's in there. We're coming up to that. And so we take a look at July and said, okay, with 500 gallons a minute, we know every tree is going to take so many gallons a day. We could actually calculate how many total trees he could plan on growing under those water conditions. So we say, okay, a cherry tree, for example, would take a full-size cherry tree might take, say, 100 gallons of water a day. And he had 500 gallons a minute. And all we had to do is multiply 500 gallons a minute times how many minutes there are in a day, divide by 100, and he knew how many cherry trees he could grow with that water supply. So it can be a very tried and true, cut and dried method of doing your planning by knowing that stuff. Then we have to look at water application efficiencies. Different systems put water on at different efficiencies. You know, the worst systems generally are flood, furrow type systems. Generally they say those systems might be average 50% efficiency. In other words, half the water is actually being used by the crop and the other half is running off the end of the field, deep percolating, or evaporating without being used by the system, by the plants. So our problems are putting on too much water in some areas for deep percolation, having some of that water run right out the end of the ditch, what they call the tail water, that's lost, so it goes down the ditch, out the drain, so to speak. And then there's that free water surface as the water's out there in the field just sitting there as a free water body evaporating off the surface of that. Water just evaporating right off that surface before it gets a chance to penetrate into the ground.